Hello, hi. Welcome to EDUHUNT, IIT and NEET foundation classes. This is Sukumar, your chemistry mentor. See, in the last class, we started discussing hybridization. From 9th class Module 1 chemical bonding chapter, I started explaining hybridization, and in that particular class, we discussed what is hybridization and what is the need for hybridization, and I explained with one example, right? Now in this particular video, we are going to discuss few more examples so that we can properly understand what is hybridization and how to determine hybridization for particular molecule or any chemical species. Okay, let's start the class. See, for suppose, let's start the class. See, for suppose there is a molecule like C2H6, right? Now we want to determine the hybridization for this particular molecule. I hope there is the central atom is, you know very well, central atom is carbon, but here there is two central atoms, right? That is two carbon atoms. And if you want to propose the structure for this Lewis dot structure or Kekulé structure, the structure can be like this, right? The structure can be like this. See, this is not the shape, okay? This is Lewis structure or Kekulé structure, which only gives the connections. It is giving only connections. In this C2H6 molecules, how carbon is connected to, one carbon atom is connected to other atoms. So this is how it is connected. Now what is important for us is what is the hybridization of the carbon here. Now we want to determine the hybridization of the carbon here. Here carbon, both the carbons are looking in similar environment, right? That means hybridization of both the carbons are going to be same. So now if you determine the hybridization of one carbon atom, other carbon atom hybridization also same, right? Yes. For that, first of all, what is the central atom? What is the central atom? Carbon. What is the electronic configuration of carbon? Outer electronic configuration of carbon. The valency shell electronic configuration of carbon can be, I will write in box format, 2s, 2p2, 2s to 2p2, right? This is 2s orbital and this is 2px, 2py and 2pz. 2s to 2p2 means you need to take two electrons, 2s to 2p2. But this particular configuration is nothing but the ground state configuration. Sir, what I mean by ground state configuration? Ground state configuration means you can take the element or atom electronic configuration when it is not in bonding with other atoms, okay? Yes. So ground state configuration, okay. But the point is, when this carbon atom is going to involve, when this carbon atom is about to participate in hybridization, it will be excited, the carbon atom will excite because it is going to have some bonds with other atoms, na? That's why the carbon atom will go into excited state. Sir, what is excited state? What is excited state? In excited state, the electron, the paired electron, one among the two, among the two electrons in this pair, you have to take one electron shifted to this orbital. Now this particular configuration can be called as excited configuration. Excited. So this is 2s, 2px, 2py, 2pz. Okay. Now try to write the electrons. One electron left here. Fine. So by this excitation of electron, you got 4 unpaired electrons. And you know very well, to have a single bond, atomic orbitals or hybrid orbitals has to overlap. the orbital with unpaired electron should overlap with the another orbital with unpaired electron. So that's why you got now 4 unpaired electron. See, all these things are happening in the valency shell of one carbon atom. Keep that in mind. Okay. Now what is hybridization? Hybridization is nothing but intermixing of atomic orbitals of nearly same energy or same energy. See, these 3 atomic orbitals, px, py, pz, these 3 atomic orbitals belongs to the same subshell, that is p subshell. So these 3 will have same energy, and this p electrons or p orbital and s orbital will have nearly same energy. So which orbitals can intermix in hybridization? The atomic orbitals with nearly same energy or exactly same energy. So these 3 are going to have exactly same energy, and this is going to have nearly same energy. So these all can intermix, no problem. Okay? Yes. But first of all, we should understand, do we need really 4 unpaired electrons here? Yes. That information you can get by the structure. See this structure. In this structure, you are going to see 4 sigma bonds. 4 sigma bonds means what happened here? Carbon has contributed its 4 unpaired electrons to the bonding. That means all the 4 orbitals has to be involved in hybridization. So simply how to show that thing in paper? These 4 atomic orbitals are intermixed. These 4 atomic orbitals are intermixed. So when 4 atomic orbitals intermixes, what happens? 4 hybrid orbitals will be formed. 4 hybrid orbitals will be formed. Sir, what is the name of the hybrid orbital? See, one s orbital intermixes with 3 p orbitals. Then the hybridization is called sp3 hybridization. The name of this particular hybridization is called sp3 hybridization. Okay, sir. How many orbitals you are getting, ma? 4 hybrid orbitals. What type? sp3 hybrid orbitals. 4. That means 4 atomic orbitals intermixed to give 4 hybrid orbitals. Now what's the difference, sir? 4 atomic orbitals intermixes to give 4 orbitals. What is the difference, sir? Yes, there is a difference. These are atomic orbitals. These 2 are different. This is s orbital and rest of the 3 are p orbitals. They are different. Their shape is different. Their energy is different. Everything different. But after intermixing, you got 4 orbitals, but these 4 sp3 hybrid orbitals are equivalent. They are, all the 4 are equivalent. All are equivalent. All the 4 sp3 hybrid orbitals are equal in all respects. Okay, fine. Next, what is important point? After formation of these 4 sp3 hybrid orbitals, they will arrange in space. These 4 sp3 hybrid orbitals arrange in space in such a way to have minimum repulsions between them. You need to arrange the 4 sp3 hybrid orbitals in space in such a way to have minimum repulsions between them. Now the point is, sir, how do we know in which arrangement you are going to have a minimum repulsion? We don't know, na? Yes. So do remember, practically or by experience, by regular study of chemistry, we got to know that when there is 4 orbitals or 4 atomic orbitals or 4 orbitals, the minimum repulsion, the structure which gives minimum repulsion is called tetrahedral. When there is 4 orbitals, the 4 orbitals will orient in space in such a way to have minimum repulsions. But what is that geometry which gives minimum repulsion is the tetrahedral geometry. Now you have to arrange these 4 orbitals in space in tetrahedral manner. 1 sp3, another sp3, another sp3, one more sp3. So these 4 atomic orbitals intermixed to give 4 hybrid orbitals. So all these are same in all respect. This is one sp3, another sp3, one more sp3, sp3. The point is, after the formation of 4 hybrid orbitals, these 4 hybrid orbitals are arranged in space in such a way to have minimum repulsions between them. But you need to memorize this, that when there is 4 hybrid orbitals, the geometry or the shape which gives minimum repulsions is tetrahedral. Okay? Yes. Now 4 sp3 arranged in space in tetrahedral manner. But the point is, these atomic orbitals, when they are intermixing, each atomic orbital is having one unpaired electron. Now each sp3 also will have that same one unpaired electron. That means one unpaired electron here, one unpaired electron here, here, here. That's it. Now each carbon, that means this is the situation of carbon before bonding with, see, if you observe this carbon will undergo this entire process before bonding with other carbon or other hydrogens. Again I am telling you, you are talking about this carbon na? This carbon is bonded to hydrogen, another carbon, okay? But before this carbon bonded to these 3 hydrogens and that carbon, this carbon undergoes this entire process. Now this carbon is ready to bond with 3 hydrogens, another carbon. So, and you know about hydrogen. Central atom, only central atom will be involved in hydrogen, not side atom. So the side atom hydrogen is having 1s1, right? Hydrogen will have 1 electron, that is in s orbital. Yes. So hydrogen, this is 1s1 with its electron, hydrogens 1s. Hydrogen atom 1s with its electron paired. Similarly, hydrogens 1s. So sp3 s bond, sp3 s bond, sp3 s bond, like that. Here carbon is bonded to another hydrogen. This is sp3 of carbon bonded to s orbital of hydrogen. All the 3 are same. Okay. Now what about this sp3? Now this sp3 is going to bond with the sp3 of other carbon, because if this carbon is undergoing sp3, that carbon also undergoing sp3, right? Yes, I will show here. Now this is carbon, hydrogen. Now what is this bond? sp3 of carbon bonded with s orbital of hydrogen. Of course, when it is sigma bond, it is single bond. Single bond, it is sigma bond, right? Yes. Same type of 3 bonds. Now sp3 of this carbon overlap with the sp3 of another carbon, and this carbon also same situation. So what is important here is, I will give a different color to this. This hydrogen. All carbon hydrogen bonds are what type? sp3 s overlap. But this carbon bond is of what type? sp3 of one carbon overlap with the sp3 of another carbon. Okay. So all CH bonds are sp3 s type, but carbon bond is sp3 sigma. So single bond sigma, single bond, all single bonds are sigma bonds only. And one more point, hybrid orbital is not involved in pi bond, okay? Hybrid orbital only involved in sigma bond. Keep in mind. Okay? Yes. So the same, see, this is giving only structural details, that means connections. But let me show the same concept with this type of diagram. Okay, I am taking next page. Yes. Now let us say this dot has a 1 carbon hybrid orbital. I'll write here. Hybrid orbital sp3, 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 right? Another sp3. Okay. Now each sp3 is having one unpaired electron, unpaired electron, unpaired electron, unpaired electron, unpaired electron. This is the situation of one carbon. Now what happens? Another carbon is also going to have same situation, but let us dot. This dot is the carbon. Now sp3 of this carbon overlaps with the sp3 of that carbon. And when the atomic orbitals or hybrid or any orbitals overlap, there is common space. Overlaps gives common space. In this common space, electron of this sp3, electron of that sp3 in this common space. Right. So this carbon also tetrahedral. Another sp3, 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 each sp3 is having unpaired electrons. Okay. Now what is this? Carbon. This is carbon, carbon. Every orbital, this is sp3, 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 sp3. All are sp3 orbitals. All are sp3 hybrid orbitals. Each carbon is having 4 sp3 hybrid orbitals. Among the 4 sp3 hybrid orbitals, one sp3 overlaps with the another sp3 of the next carbon. Okay. Now 3 sp3 orbitals left. Now oxygen 1s, hydrogen atom with its 1s orbital. 1s is having 1 electron, that paired. Hydrogen atom 1s1, 1s1. Hydrogen atom 1s1. This is 1s. Okay. Hydrogen, 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 hydrogen. Hydrogen there oka electron untadi 1s1, 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 like that. Okay. Now what about the bond angles? All the bond angles, these bond angles are tetrahedral bond angle. Bond angle is 109 degrees 28 minutes. Tetrahedral bond angle. Okay. After sp3 hybridization, the 4 sp3 hybrid orbitals will orient in space such a way to have minimum repulsion. Now, when there is 4 orbitals, 4 hybrid orbitals, what is the geometry which gives minimum repulsion? Tetrahedral geometry. And obviously, tetrahedral geometry will have which bond angle? 109 degrees 28 minutes. Okay? Yes.